Good afternoon, student of the course 4022. Here we are. Uh, we are talking about having a full PI controller using an Arduino, as shown here, and installing a thermistor within a voltage divider. So basically, the voltage from this voltage divider will get to analog pin A0, and the Arduino will do the conversion, and eventually that's the temperature that you are reading from this vessel. A little bit more on that. So what you have is the 5 volts getting here. This is going to the ground, and this is 10K, 10 kilo ohms resistor, and here is the thermistor reading the temperature from your vessel. And the idea is to ensure that we calibrate this thermistor so that we know first precisely the voltage out here, which eventually within the Arduino, as we all know, basically that signal, the voltage, which is basically a number between 0 and 5, is converted to a digital number between 0 to 10, 23. And this is what I call the ADC, analog to digital converter. So the voltage, which is a number from 0 to 5, is converted to a number eventually to 0 to 10, 23. So we need to ensure that we calibrate this guy within the range of basically from minus 25 degrees C up to 130 degrees C. All right, so we have the full range of this thermistor in place. In order to do that, a student sent me some piece of information that I really want to share with all of you, and it's right here. Basically what he did, I like what he did for doing this calibration, so that's why I want to kind of share all this information with you guys. And the idea is the following. As you can see, he did the calibration, and I will show you in a second how he did it. But as you can see, the ADC is on the X side of the graph, and the temperature is on the Y scale. And so the idea is to plot temperature versus the ADC, which come from the voltage divider, the voltage out. And as you can see, there's some different kind of regions. Obviously, try to fit the whole data within a linear regression is not possible. It will not fit the data right. So you have to divide, like for example, in different zones. Like you have one zone here, perhaps another zone down here, and maybe a last one down here. In fact, this zone here of the high temperature range for the thermistor is quite different from everything else. This is totally a different zone. So maybe you have between, I will say, between 3 to 4 different zones or areas where you can have different, obviously different correlation, different slope, different intercept, just to get the whole profile for this thermistor sensor going down to minus 20 up to close to 130 degrees C. Now, how can you calibrate for such a long range? Well, this is the part that I really like what he did. Here he started to dividing within the different zone, but before getting into that, let me show you what he did. Clearly, he says here, just to calibrate for the high temperature, he used oil, cooking oil, And here is a reference sensor, reference temperature sensor, and here is showing how he put the he wrap up basically the thermistor sensor within the reference sensor, so he get the proper temperature of the oil uh, with the reference sensor, the reference which is reading temperature, degree C, and the value of the ADC through the conversion of the Arduino is doing. So basically here is showing, like for example, at 67 degrees C, which is also converted to I'm not sure here is, I think there is degrees Fahrenheit. Yep, degrees Fahrenheit. He's showing then that the analog, or this in this case the ADC, is showing a reading of 950. Okay, and by the way, he's using an I2C type of for the LCD. It's not using the regular parallel type of connection, which is kind of nice. It simplifies the whole thing and looks a lot cleaner than when you use the connection, the parallel connection between the Arduino and the LCD screen. So going further on this, now just to get to the very low temperature, let's see, he used, let's see if we show here somewhere. Oh, here it is. For the very low temperature, he did a mixture of ice with salt, regular salt, table salt. And when you mix that, you can reach very low temperature as shown here for his reference sensor. And therefore, he's reading the ADC versus this temperature. So that's the technique that I really want to convey to all of you for doing your testing. And by the way, he has here the date when he did that experiment. Okay, and so here is just for regular temperature, a little bit higher, and so forth. But again, for the very high side, above 100 degrees, he used oil, and for the very, very low side of the range for the thermistor, he used ice with salt, a few grams of salt. You kind of shake it a little bit, and when the water start to, the ice kind of start to melt, that's when you start to get a good reading of your reference sensor, and so the value of the ADC. At the end of all this, then that's where you get all this. You get a table where between the ADC values, which are coming from the Arduino, and the temperature as shown here. Here is a little bit of a mistake. He fixed it. He sent me another data. This number is 230, which is great. And now this is the data that you are trying to identify the proper zone so that you can get a proper equation within the Arduino to have accurate reading of temperature by identifying in which zone are you talking about. To do that, let's move, this is a PDF, let's move to Excel, to the information that he sent me through Excel. That will be a lot better. Here, I think this is the right one. Let's see, 230, yeah, this is the right one. Again, this is if you plot this point here, what you get is this type of curve, which is obviously is not linear, and trying to read a linear type of regression will not do the job. So you have to identify zone, which is basically he start to do that right here. For example, he identified one zone that get to about 700, which is not bad. With a good correlation of 0.99, almost perfect. And so he has the slope here and the intercept. So that goes from 131 to 717. All right, now that's one zone. He got a second zone identified here. This second zone, the correlation is not that good. 0.97, almost 0.98. It could be better. He used a linear correlation. It might be here that you have to use a second order type of regression, like a parabola, and that will fit this point a lot better instead of using a linear regression as shown here. He also identified the zone in where this curve will be used. All right. The third zone is the one that I was talking to you, which are the last 3 points. He identified that as a different zone altogether, which is right, 0.99, good correlation, the slope, and the intercept. So again, I will say that this is okay. This one is the one that need a little bit of fixing. Not much. It's just to, to ensure that we got as accurate as we can. It's just need that probably a second order correlation will do better here on this zone. The third one, no problem. So that looks perfect. All right. So in order to do the tree zone, obviously you have to kind of break this data in pieces, right? So you have to, like for example, like what he did. Let's see. Let's see where this data come from. You see, he identified the points that he will be taking in consideration. He's showing here. I can add or subtract point depending of whether I see a good fit here, the 0.99. I like what I see, so that's perfect. I don't see any problem there. And on this one, let's see where this point come from. Those are 3 points. It's showing right here. All right. So, and the last 3 points, which are this one here. So you can, again, when you have, you observe this type of curve, you will say, hey, I might cut right here. So, like for example, on the first zone, he cut right at 50 degrees, pretty much 50 degrees C, somewhere here. So he took all this point in one line, in one straight line, which give very good correlation of 0.99. So that's perfect. Now, after this point, it tend to do more, as you can see here. Definitely a second order correlation will do a lot better, a better job. I fully agree that that would be a better correlation, starting perhaps with this point, this, and this, maybe this. You want to include those 4 points. So that would be from the 70 and above. Let's see. We have from perhaps this point, this one here. And that would be actually this one, which is 70. I can use that one. So you can do this, and this. So you got those 4 points. So let's say insert, and let's do scatter. So I have those points there. Let me move it sideways, and let's see how well. Let's compare here the data. Let's do a fit, trend line. As always, I can put a linear. Let's see. And if I take those 4 points, doesn't look that bad at all. Actually, let me set the display and the correlation. But the correlation is telling me that there's something better. 0.98, maybe 0.99. Well, almost. I can certainly do better. Let's do a second order and let's see how that looks like. Let's do that here. Format trend line. Actually, let's do polynomial, and that's order 2. Obviously, that's perfect. That's what I was saying. Is that like if you use a polynomial order 2, that will provide you a perfect fit for those points. If you want to increase the number of decimal places, sometimes you don't see the total decimal places showing here. You start, you step up here, and then you do format trend line. Let's see, actually here, format trend line label, and then you go to number, and then you increase the number of places. Like for example, let's say 5 decimal places. See, there's more numbers into it, which are very important, just to ensure that you have the total equation of how that looks like. I would say that for this project, he's perfect on the first line. On the middle, he could do a lot better with this, and then at the end, he could what he did is perfect. That will do on this end of it. Like for example, these last 3 points, they are perfect within a line. All right, it's a perfect regression what he got there. So 3 zones well identified. The only thing that I might change is that the middle zone I use a second order instead of a first order equation, and that will do. So you basically you want to use these and to ensure, like for example, let's do this actually. Let's copy this just to show you how quick I can get the equation out of where it is. You copy this, only the equation that you need. Copy. And as I said, that star about this is here, and I went to that's about 911. I can use here, so that's the number. So if I do this equal and paste, copy this, so I pretty much have the equation. Obviously I need to work on it. Like for example, I only need to multiply this by the value that is here, and remember that that's to the square, and I do the same with this one, and I multiply that by that number, and then add that, and this is the value. You see, let's move down. 93.13 is a little bit off, almost by 3 degrees. How about this one? 3 degrees still. Maybe I don't have enough decimal places. Let's check if this has all the decimal places that it can provide. And let's see. Step there. Let's increase. Let's put 10 just to see. Wow. Sounds like let's see. Let's do it one more. See whether I have an improvement. For copy all that, and then step here. Delete that one. Put the new one with more decimal places. See whether there's an improvement. Do the same again. Times this value. Square. And times this value. There we go. You see what I was saying? Has to be very, when you have something to elevate it to this power, you have to use all the decimal places that you might get just to get the, it was kind of strange. I was not getting the right value when I saw the correlation is so high. So you have to be careful, and that's very important. So as you can see, this is what I got from using this equation with all the decimal places as shown pretty much here. All right. So you can do you can do the same and try to find out how well this equation, which is the third zone that he identified, how well it works. Step there, you pull that up. I'm not sure whether they have all the decimal place. Actually, this is the zone in the middle. No, that's the one that I cannot substitute. So will be this one. All right, let's see if I got all the decimal places. Again, do this format, go to number, and you might want to add more decimal places. Let's see, 5 decimal places. Maybe you don't want to use the comma, just because tend to confuse. So I have more decimal places, you see. I can add more. Let's say 10. I would say that is more than enough. Let's move this here, and maybe up to 7, 2, 3, 7 maybe, and that's 5. So I will cut this 0 to a 1, and that will do. You can check that and see. Actually, let's do that, and let's wrap up this video. Let's copy that one, and that's the last zone. That's the high zone. Let's close here, and let's put it here, equal, and that's perfect. So I multiply that one times this value, and let's see what happened. 129.6, that's perfect. It's close enough, so I can drop this down here, and that's 120, 121. That's the 1 degree error. This is 110, 110, pretty much 110. Yep, that would do. And this is zone 2, and so forth. What you have to be, let's say that what happened if you get a value between 936 and 911. That's you see, that's that you have to be. Let's see if I can see that. What would be better when you are in the transition zone between this line and you have another line coming this way? Which one of the two will you use? I will say, let's see, let's think about it. This line will predict one value, and this line going up might predict another value. Let me think about it. So thinking about that, when you are within that range, like for example, what will happen if you are between 936 and 911? To which zone you are? Are you in this zone, or you are in the straight line? Let's open something here just to do that very quickly. Like for example, this is what I'm saying. What will happen, insert, if you are like, for example, in 920. Let's say if you go from here and you do a check there. Actually, sorry for that. Let me do an undo here. Here are the correlations. So let's drop there. 90. Obviously, that number is totally wrong. She could not be 90 will be like 889. So this correlation only works for those 3 numbers, and that's it. So this is not right. So let's test 100. So it should be above 100. When I go up 15, that makes sense. 15. That's the temperature. 15. If it's like I'm right here for, you see, between these 2 numbers, and that will be above 100 and less than 19. That's the 920. So it's perfect, meaning that this equation, which is square, a polynomial of order 2, is doing perfect on that region, on this region that is right here, up to basically up to 936. And after 936, then you take this equation will take over. Okay, so you establish very clearly that anything below 936 will belong to this equation here. Anything 936 and above will belong to this straight line. All right, so that will do. Now, what will happen? The same here on this region here. Let's talk about that region there for 1 second. He said that this is the equation that he's using for that region. Let me ensure that I got enough decimal places there. So let's format that trend line and let's go to numbers and let's increase the number of decimal places at least 5. Let's see what happened. Maybe more. I'm not sure if it's taking it. Nope, it's not taking it. Let's see. All right, let's do it again. Format 7. I don't see that it's taking the. Let me redo this part here as I have it, just to ensure that the trending is working. And let's redo the trending. And this and this. And let's see if I can get numbers and increase it. There we go. Somehow it wasn't working. There we go. Let's put maybe 6. Let's see. Good enough for me. That will do. So what we have to do, remember this covered from close to in the low region, low temperatures, up to a little bit above 700. And let's see the intercept, how that looks like between the two curves. I need this information only. Copy that and put that right where it belongs to. See, the data gets to about here. So I can drop this one here. And let's see what we do. Actually, that 70 belongs to this one. You see? Perfect. How about the 60? Can I drop this one more? The 60 is way off, too off. So I would say not there. How about again? Let's take a look here. The data that I was kind of looking at up to. So we need to talk about that 780. Let's see where it fits the best. To whom belong? To which of the equation? Let's paste here the equation that I have, and let's fix it. That x times this value here, and that will do. That's 50. Yeah, that's perfect. Let's go down. A little bit of coming down here. I would say up to 10 degrees looks good. 5, 3. It can get better. Maybe, but not bad. I mean, 49. I would say let's see if I can go up and get better. No, both are not good. Coming down, predict one thing, and let's see. Let's go here 1 second, and let's see if I can add one more point to this curve and see whether it gets better. It is still 0.99, so let's see if I can go one more point above, like include the 60, and let's go up here. There we go, and drop it here. There we go. And now let's go back and see. And let's do the correlation again just to ensure that it looks good. Trend line. Let's put the display and this. It's still not bad. I mean, it's going up already there. I can see the point higher than the line. But again, it's just that I'm trying to avoid having another 2 zones within this region, which makes sense to me. Let's increase the number of points. Let's do the format, and let's change numbers, and let's increase it to 6. That's good enough. Copy that. And now let's close this, and I'm fixed now that I'm about 60 degrees. That change right from here. So let's do equal, and that need to be multiplied by the ADC, and still 58 versus 60. I improve a little bit. The 10 makes sense, the 8, the 6, the 5, the 3, 2.4, 1.1, 0.3. Kind of bother me a little bit, this region here, but again, you are just trying to get as accurate as you can. You could use, I mean, like a lookup table at the end. Uh, you know, like for example, if you get a value of ADC of 210, then you do an interpolation between these two numbers and these two numbers. So you do interpolation, and you get the temperature right. That's one thing. However, you need to put all this information within an array within the Arduino, and that tends to consume a lot of memory. Uh, but that's an alternative. Yeah, you could use a lookup table to get this right, or even better, do that what I'm doing right now. But I would say, as you know, as I'm wrapping up this video, uh, let's see. I think that I have all the region there. Basically, three zones. This right here, that this is the result of the equation. And let's look at the difference. Let's see the difference. Let's see the difference here between the absolute difference between what the equation is predicting versus what I actually have here. All right. So, and let's go from there. And let's take a look. This 920 was something that I add, so I can delete that. There we go. And this is the actual data. So here is the the one that we were talking about. Which equation predict better? That's the 60 degrees is where I might have the largest error if I use that correlation the way it is. And again, back here, the difference here, then it kind of dropped. The worst is definitely here in this region of where is the minus 16.6, and you can see that the points are here a little bit. These 2 points are kind of on their own, making their own zone basically. So you have these two. So you might need to get these 2 points out. Maybe that might improve a little bit. So the correlation will end up to be a minus 10. That's an alternative. Eliminating these 2 points and just getting up to here. If I do that, that's the zone, this zone here. Let's see if I got a better correlation. I doubt it, because this point is here. I need these 2 points here just so that I can get the best straight line, if possible. Maybe a different correlation might help here. I don't know. Let's say that let's redo this just for the time being. If I do second order correlation, and I'm gonna eliminate that fit there, and let's put a new one, and let's do, instead of linear, polynomial, and that's order 2. And let's see how better, whether I got an improvement. I don't see much of improvement. Still 0.9948. Can I use a higher order? You might, certainly. Obviously, you get this is more complicated, more terms on your equation. Let's try just for the sake of the argument. Um, let's do again this here. Order 4. 0.9996. Maybe that zone looks a lot better now. 0.9996. Be extremely careful with the decimal places. Seems like now I might go through all the points, and let's check that out. Let's step here and let's increase. Let's see. Let's format that trend line label. Let's go to number and increase it to 6 maybe. Let's see if I got any difference here that need to be adjusted. 10. Since I'm not writing this number down, I don't really care how many decimal places they put up, because I'm just copy the equation the way it is and paste it what I needed, and that's it. You can certainly do this like this. You don't follow that too quickly. You can use scientific notation, and you get a bunch of pretty amount of decimal places just to ensure the best accuracy when you do the points. Actually, that might looks good. Let's test that. Let's copy this. I need to copy up to here and copy. And now be careful here what I'm going to be doing. This is for the low region that start at about 70 degrees here. Used to be, I think that I used on a square equation there in one point in time. Let's see if I go down. Actually, the 70, yeah, the 70 belongs to zone, the middle zone is this one here. From the 60 down and down. Drop again. Let's take a look at it. Yeah, from the 60 and below. That's the first zone. So what I need to do is step here and do the paste. Obviously get one of these equal sign, delete it, and down when it says here times, that would be the value, this one here, to the 4, and that will do. And do the same for this one here, time this value to elevated to the 3. Now do the same of this value here, elevated oh, actually this one here, elevated now to the 2. How about this one? Is easy. Let's multiply that value by this one, and I think that I got everything. Perfect. 60, 60. How about if I drop down that equation? Ooh, now we're talking. Now we're talking. See? The difference is less than, basically the higher number I can see is this one here, but it's in the very low zone, but everything else looks perfect. I would say this is it. I call it right there. So 3 zones basically. This zone basically to the 4, a polynomial order 4 to get all this point in a straight line, and in the middle I use you cannot see this one actually, is this one above right here. I use this correlation, the order a polynomial of order 2, and at the end I agree with him. I use a straight line, and that did the 3 zones, which basically provide pretty good result, pretty accurate. So I have basically, I end up with 3 zones for doing the correlation. All right, that it could be improved. I mean, you can certainly improve this to get that a lot better. All right, but I will leave this the way it is right now. And so basically, I identify 3 zones. The first zone, this area here, I use a polynomial of order 4 to get most of the points in, and then on the second zone I use a polynomial of order 2, and in the final zone I leave that as a first order correlation, just a linear regression, and that kind of did the trick. So what you will do now in the Arduino is just have 3 equations. Anytime you call for the temperature, you need to check with an if. If the number in the ADC is 936 and above, then you use this one. But if the number is below 936, up to, I would say that number was right here, up to, you see, above 780, up to 780, I will use again, what would be better on between the 780 and the 824? Let's open one window here and let's take a look at it. Insert, and let's say that I'm right at 800. Which one provide the best equation? This tell me if, in fact, I think that it used this equation here. Yep, it provide me that would be 66 coming down. If I go up, let's go up with this one. Let's see what it provide. 64, 66 as at 800. Let's do. I can certainly do a linear regression just to estimate what would be the actual number that I need right here. Let's do what I will say I will do is an interpolation, and let me do that. So let's do the interpolation right here. Let's put an equation here that will do the interpolation. So this is what I want, but I know this value and I know this value with this temperature. So let's see what 800 will produce here. Just to do that, let's do open a parenthesis. That would be this minus this divided by the total range, which is this one minus this one, and that has to be multiplied by the total range of the temperature here, which is this one in the same order minus this one, and then you need to add this value here. All right, it predicts 65 degrees. That's interpolation basically. The question is, which is better? Which equation will produce this 65? That might be, let's drop this. That predicts 66. This predicts 65. Actually, let's get here the difference. About 1.2 degrees difference. If I go up, let's see, on that range, that is better. See? So that kind of settled this out. So I will say the 824 seems to predict this 70 is better, is what I call the zone 1. You have 1, 2, 3, 4. This belong, let's put a word here. This is zone 2, and this one here too. So I can say up to here. Sorry for that. That should be a 2. Actually, let's see if I can get this right. There we go. Now here, this is the last zone. This is zone 3. And so this one. And so the last point here. All right, and from here and down, obviously this is an interpolation, so it shouldn't be a problem. But actually, let's start from here. This is zone 1, and that 2 here. And again, let's do this so that it doesn't screw up my. There we go. This point might be you might delete it. You want to, but again, what I'm saying is delete. Basically, when you have here zone 2 starting from 824, that means that any value that is below 824 belongs to zone 1. All right, so that's important. Establish the range of where our equations are valid. So let's do this here. So we get this to a close. What we are saying is ADC range, and what is the zone? Sorry for this. Let's fix this. And what is the zone? Like, for example, if you are from 131 to I would say including, for the zone to work, you have to be from 131 to less than I think it was 824. Have to be less. So, and this belongs to zone 1. Now, if you are 824, but let's see how that work out. But let's see, zone 1, zone 2, and we are saying have to be less than 936. Yep, that's what I'm saying. Next than 936, then you belong to zone 2. Now, if you are 936 or above, higher than 936, you can do this like this if you want to. Equal 936, equal or above, then you are in the last zone, zone 3. And those are basically, again, the 824. Let's see if I can fix that 824. The 824 belong to zone 2, so it's right here. If your ADC is equal, one way to do this better, right? If I can, let's open this. Let me do this a lot better than what I'm doing right now, so nobody get confused. What I'm saying is, if your ADC like this, if your ADC value is above 131 but less than 824, you are in zone 1. If you are now between 824 inclusive but less, I can certainly do this, less equal ADC but less equal, I'm not sure that 936 is included. Let's go up again. The 936 belong, no, cannot be. 936 belong to the third zone. So if you are below 936, you are in zone 2. But if you are equal, if your ADC is greater or equal 936, you are in zone 3. That's it. And that's how will you fully calibrate your sensor with at least an error, I will say, within plus minus 1 degree in most cases. Like for example here you can see 1 degree different, but it looks good. It looks good. So you have the full range with these 3 equations, which are very easy to insert them within your Arduino. All right, have fun. Thank you, and as I always said, be safe, whatever be your final destination. Bye. Wow, I was about to leave, but all of a sudden I said, let's check the maximum correlation that I can get from Excel, which is a polynomial of the order 6. And it produced all these parameters that is here. Again, I don't have to copy them by hand. You just copy and paste it where you need them. And here is the value that it produced. This is by the equation, order 6. And this is the absolute difference. I'll put the difference here, the absolute difference. And obviously at the high temperature, 130 here, you can see the equation here, huge. 130, 120, 110, kind of not so good. But then after that, like for example, at 100 degrees, I would say it's keep within about 0.5 degrees, and it can drop to pretty down. Basically, it do a pretty good job from minus, I would say minus 16 degrees up to about 100. So everything can be with one zone, unless you are expecting to hit, to kind of heat the solution to above 100 degrees. I think that you are pretty much good with this. I mean, with only one zone, and that would be from 0 to 100, and it would do a pretty decent job. Only one zone. Obviously, the equation is huge. You will have to deal with all these, typing all that within your Arduino environment, which is not a big deal. I mean, if you open the Arduino code and you just need to copy all that, and so let's do that very quickly. What I'm saying is you open your ID, and I don't have to do anything by hand. Let's wait until I get my Arduino code right here. And here's the version that I'm using, that's 2.3. Like for example, this version only uses one equation, so you want to be, you see right here, where it said verificar su calibración del Thermistor. So here I will add my equation right there. So I copy what I need to copy, and PV is the value coming from the ADC, that's the average, and this is a linear correlation that I'm using for all the zone. Remember, what we said is that we have to limit the temperature to where the thermistor is linear. If you want to expand above and beyond, you gotta be careful what your equation that you are using. Like for example, right now I might use something like this. Let's bring the equation back. Let's go to Excel for 1 second, and let's copy the equation. It's right there. So I copy all that, copy, bring it to my paste it here, and let's say my new PV is that one, equal. Now whatever is an A2 here, you just substitute by PV. You see, since I use this equation several times, the better will be to use kind of a void subroutine. That will do the trick easily. So you just, anytime that you need to put your PV in engineering unit, you call that subroutine. or that function. It's a void function because the parameters that I'm using are global. So you could use a function just to get the PV value converted from ADC unit to engineering unit. But the nice thing is that I don't copy anything. I just, type whatever I have to. Like, for example, this A2, the only thing that I need to check is put a PV here and put a PV here. And now, careful. This is elevated to the 6th. Then you cannot do that in Arduino directly. So what you have to do is get the instruction power. Power, let me show you how would you do that, because this will work in Fortran or any other compiler, but for the Arduino you have to power in Arduino. See, POW. That's the instruction that you need to use. So as I was saying, basically you take the ADC and you elevate it to whatever exponent that you have according to your correlation. Like, for example, going back here, you see you have this number, and then you need to multiply that by your ADC, right? That is coming from this column or from your Arduino, but you have to elevate the ADC to a power. So, and that you multiply by this number. So going back to here, so that's what you have to do. Let's go now to my IDE here, but here's the deal. This is the part that you need to be careful, because this is the one that has to be by the power now of what? But then put the parentheses. A3 change, obviously this is coming from Excel, but that's my PV, which is my average value coming from the ADC, but that need to be elevated to the power of 6, and that's it. See, so basically you copy this piece here, and every time you see this one here, the only thing that you have to change is put this to the 5. Now change this again to the 4. Change this one to the 3. Change this one to the 2. The last one doesn't require anything, just multiply that by PV minus then the constant number, and obviously you are programming, you need that there, and get one of these that is, and now you have your equation pretty much ready with one zone only for getting the temperature from around 100 degrees down to, I believe, about 0 degrees, between 0 and 100. One zone, that will do. And you can, for the time being, comment that line, and then you have this new one that will do the conversion in a kind of a pretty much the whole range that we would like to do that. Now, I'm not using a function here. Be careful. Every time that I call for engineering unit, you need to look for that humongous equation, and like, for example, you have it right here. Be careful. You see what I'm saying? That is better to use a function, a void function, just to get that. You need it there. You also need it here. You also need it here. And I think that you might need someplace else. 3 places basically, or 4 places. That's 1. This is 1. This is 2. This is 3, and obviously in the place that I was working on it, and this is 4. Okay, so as I said, an equation so big like this one is better just to have it as a function and call it when you need it, and you are done. Again, that will do. Let's leave this one in comment, and let's use the one that I had before, but I'm going to save this, and for a next occasion, if I want to use a kind of a larger range on temperature, this equation will provide that to me. Remember, the only problem here is that this equation that I'm showing here is for the thermistor for this particular student. Your thermistor might be a little bit different. You see, might have different numbers and so forth. So that's why every thermistor must be calibrated, just to ensure that you get good engineering units as you do the conversion. More than enough. Have fun, and that's it. Bye.